This is the third part of Lecture 4 in quantitative big imaging, and we are continuing talking about segmentation. Now we are looking at some approaches that we take from machine learning and see what that can help us with our choices in selecting thresholds to segment our images. So, first of all, we have a lot of steps following up. We already talked about filtering, and then we needed to look at the histograms, and some is actually also very specialized to machine learning and how to work with it. So let's look at an important problem from electron microscopy. And here we have an image of cells, and we want to find the mitochondria in this cell. And in this case, we actually have the raw image from the microscope, and we have a ground truth. So someone labeled this image to mark up where we have the mitochondria. And now our task is to identify to which class each pixel in the microscope image belongs to. So what we want to do is to classify pixels that belong to the mitochondria as foreground, that would be in this case white, and pixels outside would be background, and now we have black here. So which values can we assign? So we can categorize the values into true positive, which is we have a mitochondria and it's correctly classified. Then we have true negative, which is when we are outside of mitochondria and we classified it as a background. But unfortunately, there are two other cases too. One is false positive, where values outside the mitochondria are classified as mitochondria. So that's classified as foreground. And we have a false negative, which would be mitochondria pixels that are classified as background. But how can we know which one is right or wrong? And this is where we again need to look into data sets and having the availability of a ground truth that actually someone was sitting down and marking up. And that goes back to lecture 2. And the first way of doing a segmentation is to apply a threshold. Very simple. So what we do is we have the image, we compute its histogram, where we, in this case, can see that we have 2 bumps in the histogram. And now is the question where to put a threshold, and that is our separator between background and foreground. In Python, you implement this by setting a value for the threshold, and then we compare each pixel in the cell image with this threshold, and out comes a bi-level image, black and white. So if we apply this threshold, which I have set now to 0.52, then you can see there is a lot of pixels which are not really mitochondria according to the labels, so we have a lot of misclassifications here. How we can get rid of these is something we will look into in later lectures, but leave it like this for now, that we do misclassifications, and now we want to measure how many it is that are misclassified in some sense. Oops. So, and what we can do is we can look at which true negatives we have, which false positives, and now I already set this up into matrix form, and maybe if you remember from lecture 2, we had the confidence matrix, and that one we can now look at confusion matrix, sorry. Here we have the matrix. I have colored it up nicely, so you can see that we have true negatives in this corner, true positives in this corner, and as you can see, there are some pixels that are classified right, but on the other side, we also have a lot of misclassifications. In particular, we have classified very many background pixels as foreground. And this we can also see in this heat map, where I have color-coded the different cases. So this dark gray and white corresponds to what we expect. And red and blue, they correspond to the misclassifications. And here we can see that we have a lot of red, which actually corresponds to also the 32% that we can see here in the confusion matrix. The blue is inside the mitochondria, so we were not really certain about what we have. And then you also get some misclassifications within the mitochondria, and that gives us something like 1.5%. So this is not really a good result, but we can actually visualize and get an idea that, first of all, we have to conclude, okay, we need to do something better. And these are nice tools to actually see this. And as you can see, the confusion matrix is quite limited in information where we have the information. And then the heat map can actually tell us that the mistakes are all over the place and they are not localized to just the boundaries of the mitochondria. Two metrics that we are using are precision and recall. And recall is the ratio between true positives and false negatives. So that would be the number of positive classified pixels as we got them, divided by the total number of expected pixels in this class. The precision is the total number of pixels classified, a true number, true positives, divided by all pixels classified as foreground. And this can be calculated, so I have printed it out here. And you can see that the recall is 0.82 and precision is 0.18. And both numbers are not really convincing. So let's see another way also to actually visualize how the performance can be plotted. And that is, there we have something called a receiver operating characteristics curve. And in the beginning, it was actually developed during World War II, and it was related to detecting objects on the battlefield radars. And if we have a single value, then we can just compute the recall and precision for it, but it doesn't really tell us if we can get better or worse. And the ROC curve actually tells us the relation between precision and recall for the current segmentation model. So let's compute some hit and miss statistics. Here we have a table with different thresholds, and it's computed also the precision and recall and false positive rate, and also the whole counting here. And actually it's repeated all the time, but it's recycled. And now we can plot this table. First, we look at the single value, and here we can see that we have our precision and recall for a certain threshold, and that gives us this point. Ideally, this curve, you want to be here, that you have very good true positive rate and no false positive rate. Naturally, it's not possible. So let's see what actually our model currently is giving us. And here you can see the ROC curve, which we can import from scikit-learn. Actually plots out like this, that in the beginning, of course, when we set the threshold low, and that we can look at actually, if we go back a little bit to the histogram, you can see here, if we would put a low threshold, we don't expect anything to be good, because if at a low threshold, we would say everything is foreground, and that doesn't make sense. So let's go. Oops, sorry. Let's go back to our curve again. Here. In the other case, when we are on the right side of the histogram, then of course we do everything correctly, but we also have very high false positive rate, which we also don't want. And the curve shows us now that we have this knee here, and probably we have to decide what we actually want to accept in terms of true positive rate and false positive rate. And let's see what the effect is if we now would try to manipulate the image a bit. And manipulation comes in the form of applying different filters. And the first choice is having no filter at all. The second choice is to apply a Gaussian filter with some width. Then we try something a little bit wilder. So that is difference of Gaussian filter. So we have the original image minus the Gaussian, quite wide Gaussian actually. And the last one would be applying the median filter. The code below here is a smart way of packing it. You can look into it, how it works, but in principle here we have the names of the different functions as a list, and that list is iterated, and then we call each of these filters when we iterate over the different subplots here. And you can see that the no filter is what we had before. The Gaussian is a little bit more blurred, but also less noisy. Difference of Gaussian filter, then all of a sudden you have a high pass filter, and that means we have very strong focus on the edges. The median filter is something between the Gaussian filter and no filter, so it's also taking out the noise and possibly some outliers. And now let's see what the RSE curves look for all these cases. First, we start with a random guess. That would actually go just as a straight line from 0 to 1. And we usually don't want to be below in this area, because that means we are worse than just random guessing. And it appears that the difference of Gaussian actually is worse than random guess, at least in the beginning. The other three, which apply some kind of smoothing, they do a better job. So they actually come closer to this upper left corner. And in our case, it seems like the Gaussian filter is the one that gives us the best result. Followed by the median filter, and then we have the original. So it seems like in this case, it actually can be beneficial to apply some kind of smoothing. That means we will have better separation between the two peaks in the histogram, and that also makes it easier to do the segmentation. These curves are a little bit difficult to quantify, putting a number on this one is better, this one is worse. And what is used is a metric called area under the curve. So what we do is we compute the area under each of these curves, and then we can see with a single scalar a quicker value. And this is actually one of the metrics used in machine learning when you train a model. And the better value you get of the area under the curve, the better you are. So in this case, we have the Gaussian filter, which has the best value. And the other ones are slightly after. And finally, the difference of Gaussian is not really convincing. Sometimes you have materials which are not just foreground and background, but you have multiple faces. It could be that you have, for example, different kinds of tissues. You can have maybe rocks and water and pores and something like that. And then you want to segment all three faces. And doing this can be done by putting in more thresholds. And here we have some shale, which was made as a synchrotron tomography image. And we want to see different phases in here. We want to see clay, we want to see rock, and we want to see air. And maybe from the naked eye, you can probably distinguish that we actually have three classes. We have the very dark one, which would be the void and the air. Then you have something in between, which is a mid-gray color code. That is probably the clay. And then finally, you have some very bright spots, and that corresponds to the rock. And let's see how we can do this. First, we look at the histogram. And to be honest, this is not the easiest histogram, but we can probably guess that in the lower part, you have probably the air. In the upper part, you will have the bright spots. And in the middle, as this is a large mass, you will have the clay. So let's put some threshold. Let's bring them in and see what happens. And we now give the different three classes. We have void, we have clay, and we have rock. And we put thresholds at 0.3. Between 0.3 and 0.5, we have the clay, and everything above 0.5 is rock. And now we can do some segmentation on this, and you see what the resulting images are. I would say it makes sense because we have here the dark regions which correspond to these white spots. That's good. In between, you can, for example, look at this region up here in the upper left corner. There, if you look in the original image, you have some bright spots and you have some dark spots. And that's actually also holes in the clay image. And that clearly makes sense. And then we have the rock, which only has pieces up here, but barely anything in this range where we had our voids. Now is the question, how do you really implement thresholding? We saw the first way already in the beginning of today's lecture, that you more or less just compare a NumPy array with some value. And that is actually also what you do when you work with NumPy and with MATLAB. And with this approach, you can actually also do more complicated things. So for example, we have a gray image and check if that is more than a threshold A, and at the same time, it must also be less than threshold B. And that would correspond to our multi-phase case for the clay. If you don't use NumPy, you can also implement it, but then you need to use something called a lambda function and a function called map. And what it does, it compare every pixel in the image from the gray image, and then you take that into the final image, and that's mapping out. But this is, I would say, overly complicated when you can just use NumPy in this way. If you would work with other languages, then you can't rely on the fact that you would have already nice arrays that have a lot of help functions on them. So you may have to go through the image using loops. And in that case, both for Java and C++, you have to write a loop for each dimension you have. And in this case, it's even cropping out a certain region of the image. So we go from xmin to xmax, ymin to ymax, etc. And in here, you compute the position in the array. And from this position, you do the comparison. It goes the same way with C++. The only difference is how you define the array. And I see here is, no, that is true, that's correct. So you need a pointer to some memory position where you allocate a lot of memory. If you want to work on the whole image, then you don't need to do loop from min to max, but you can actually just take a single loop over the whole data set, which is much easier then. And then you can actually, I think you can even gain some speed by that. And with all these operations, we don't consider the pixel neighborhood. We're just doing pixel by pixel. So now we come to the end of the basic segmentation, and it has shown that we can actually use validation methods to get scalar metrics to tell how good our segmentation is. And in some cases, we realize, okay, the single threshold may not be good enough. We need to look for something else. That something else is actually what we're going to talk about next week. And yeah, I'll save that for then. But in order to use these validation methods, you need to have a ground truth for the validation. It's also possible to do multiple thresholds, but also there are a couple of pitfalls which I will address in a later lecture. And the implementation, how you do it, depends very much on which programming language you are using.